In 1931, Germany decided they wanted to build a blimp. So they did. And in 1936, the Hindenburg was born. But there was a problem, that problem being the US's monopoly on helium and their long-founded hatred of Germany, meaning the German engineers had to settle for the next best thing to make their blimp float. Hydrogen gas. And for the most part, it worked just fine. The gas weighs in at only 2 grams per mole, considerably less than the nitrogen and oxygen-rich atmosphere of the Earth, which averages a molar mass of about 29 grams. This means that each mole of hydrogen, approximately 22.4 liters worth, would effectively weigh negative 27 grams, meaning that lifting the 242-ton or 219,350,000 gram airship would require about 8,124,000 moles of hydrogen. Luckily, the airship had a capacity of approximately 200 million liters, enough to fit around 8,900,000 moles of hydrogen, well enough for the airship to lift itself off the ground. But there was a major problem. Unlike helium, the noble gas, hydrogen is incredibly flammable. And, in the most dramatic of ironies, after a successful 3-day trip across the entire Atlantic Ocean, the Hindenburg tried to land in New Jersey. No one seems to agree why there was a fire, how it started, or even maybe who started it, but we all agree that there was indeed a fire. But why was there an explosion? Well, that all comes down to pressure. I'm sure we all know about the 5-point ratio describing how gases interact with their surroundings. Pressure exerted on the container times the volume of the gas equals the amount of moles of a gas times the unit of pressure constant times temperature in Kelvin. We know what the volume was, how many moles of hydrogen there had to be, and the maximum number of moles there could have been. We know the R value, 0.08206, meaning the resulting pressure will be in atmospheres, which I think is the easiest metric to put into perspective. And I couldn't actually dig up the weather reports in New Jersey on May 16, 1937 when the airship landed. The newspapers were a little bit caught up in something else, but let's assume it was a solid 20 degrees Celsius, or 293 degrees Kelvin. Plugging in those numbers, then rearranging it like this, we find that the hydrogen gas trapped in this cotton and gelatin skin had a pressure of anywhere from 0.97 to 1.07 times that of the Earth. But then fire happened. And fire is hot. Very hot. But hydrogen fire is super hot. We're talking 2,254 degrees Celsius hot, or 2,527 Kelvin hot. And hydrogen fire spreads super quickly, meaning the inside of the Hindenburg heated up pretty much instantly, causing the gases to expand rapidly and significantly. How significantly, you ask? Well, plugging 2,527 degrees back into our original equation, we find an interior pressure of anywhere from 8.4 to 9.3 atmospheres, all in the matter of seconds. And the cotton jello skin of the Hindenburg wasn't nearly strong enough to withstand this change in pressure, nor was it flammable enough to melt a hole quick enough for the hydrogen to safely escape. And thus... That's all for today, kids. Tune in next time on Ethan Teaches Chemistry to find out... how wet is water?